Hi, my name is Stella, and in this video, I'll be talking about our recent work on portable quantum language models. We have 4 motivations for this work. First of all, previous work investigating the privacy and security concerns of pre-training data has shown that when prompted with the start of a street address, language models such as GPT-2 could return the exact training data and expose personal information. Although some work has been done in the area of safe generation, the security of the training data is still an underlying problem of pre-trained language models. With quantum encoding, random quantum circuits that are irreversible can be used to construct irreversible language models, and such models with quantum circuits would potentially provide a privacy guarantee. Secondly, quantum computing provides exponential speedup compared to its classical counterpart. This is because of the amount of information that can be stored within the qubit compared to the classical bits. This also leads to our third motivation, which is that quantum language models would have more expressive power thanks to the entanglement stage of quantum encodings. Therefore, they would be able to encode more complex information with the same amount of parameters, which leads to the design of more efficient models. With all these theoretical advantages, one limitation of quantum computing is the specific hardware and environmental constraints. Unlike current pre-trained models, it would be impossible to download the entire model to a classical machine due to different hardware and different temperature requirements. Our work introduces the possibility to easily transmit information from the quantum pre-training stage to the classical machines for various downstream applications, making the quantum models highly portable and more accessible to researchers for different uses. This figure shows the overall pipeline of the decentralized quantum language model. This figure shows the overall pipeline of the decentralized quantum language model. We first start with the data on the classical side. The data is then encoded to the quantum states using various quantum encoding schemes, and then it is transported to the NISQ servers where the quantum language model is hosted. The language model is built with random quantum circuits that provides irreversible training. And the key to the portability of the model is that only transferring the trained embeddings would be sufficient for downstream tasks. In our work, we define ad hoc portability as only transferring the minimal necessary information from the quantum language model to downstream tasks, which allows for more efficient pipeline designs and increases the accessibility of quantum language models. Our proposed solution only transfers pre-trained embeddings to initialized downstream models so that the majority of the model can still be hosted, can still stay on the quantum side without the hassle of transferring it to the classical side. Due to limited computing resources, our experiments were done on small LSTMs with all the gates replaced by random variational quantum circuits. The number of parameters for a 4-qubit system is about 150. This is a tiny language model, but we were still able to show that its performance is comparable with a classical language model with the same number of parameters. A little bit more about the variational quantum circuits. There are 3 major components of a VQC, and they're the encoding stage, the circuit stage, and the measurement stage. In the encoding stage, classical data is encoded into the quantum space. In the circuit stage, the random combinations of different entanglement strategies take place, and the parameters are stored and trained. Finally, during the measurement stage, the quantum states are projected to its eigenvectors to get the final output. To evaluate our model, we looked at the loss and perplexity as well as downstream performance on the sentiment analysis task. We used 2 publicly available data sets that are already labeled for sentiment analysis for the training of our language models. The data sets are linguistically complex in the way that they're either multilingual or code mixed, and we hope that our quantum language model is able to capture the intricate linguistic complexity contained by the data sets. Looking at the model perplexity on the multilingual tutor dataset, the quantum language model converges at a perplexity similar to that of the classical one with a similar number of parameters. When we increase the model size by increasing the number of qubits from 4 to 6, there's a large drop of perplexity. Furthermore, the quantum language model converges significantly faster than the classical one, and the classical model has a smoother loss curve, which is expected due to the stability of current classical computers compared to the quantum simulations on the NISQ servers. Comparing the quantum language models with different sizes, we can see that the 6-qubit model reaches a lower perplexity at the end, while both models converge within the first epoch. Lastly, the quantum language model and the classical language model show comparable results on the sentiment analysis task with only using the trained embeddings, demonstrating its capability to be applied to a variety of downstream applications. In summary, our work strives to build secure, fast, and expressive quantum language models, and we propose the concept of ad hoc portability to increase the efficiency and accessibility of quantum language models and its applications. We hope our work opens up more discussions about using the unique advantages of quantum computing to solve various current NLP problems. Further research directions include more in-depth explorations of quantum circuits, theoretical proof of privacy during pre-training, in addition to current empirical testing, and finally, scaling quantum language models to larger attention-based architectures such as BERT. Thank you for listening, and you can find more detailed experiments linked by this QR code on the slide.